All right, so in our last video, we were looking at the remainder and factor theorems. And now in this video, we're going to be using those two theorems together, working with the rational zero theorem to help us find the real zeros of a polynomial function when it's in its expanded form, okay? So for you to use the rational zero theorem, you have to be working with a polynomial function of degree 1 or higher in a non-factored form. Okay, that's what this notation right here is stating. Okay, your function should be in a non-factored form, and basically what the theorem says is that um, if P over Q in lowest terms is a rational zero of f, then that means that P has to be a factor of a sub 0 and Q has to be a factor of a sub n. So basically we're saying that in order to be a rational zero of the function f, okay, the numerator of that rational zero has to be a factor from the constant of the function, okay? And then the denominator of that rational zero has to be a factor of the leading coefficient of the function, okay? Now, what I want you to understand is that this theorem doesn't directly give you the rational zeros of the function. It just gives you a potential list of the rational zeros, okay? And then that's where the remainder and the factor theorems come into play. If we can come up with a potential list of the zeros, then we can test them using our remainder and factor theorems to see if in fact they are actual zeros of the function. Okay. Um, Also understand that while this is referred to as the rational zero theorem, it's also a factoring technique, okay? This is a way of being able to factor a function when you don't know of any other technique to work, okay? So let's use the theorem at play here. We want to find the list of potential rational zeros for f of x equals 2x cubed plus 9x squared minus 20x minus 12, okay? So basically what the theorem is stating is that we first and foremost want to focus on the constant of the function. And this constant is going to lead us to a list of p-values, and it would be all of the factors of negative 12, both positive and negative factors, okay? So that would include plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Those are all of the factors of the p-value of negative 12, okay? And then Q is going to be coming from your leading coefficient of the function. All right, now that's prime, so the only factors of 2 would be plus or minus 1 and plus or minus 2, okay? And again, what the theorem says is we now need to combine our p-values with our q-values to make this fraction p over q. We need to come up with every possible combination of p over q, okay? So if I take each of the p-values in blue and I put them over the red q-values of plus or minus 1, they're going to stay as plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Okay, that's taking all of the blue numbers and putting them over plus or minus 1. Okay, now I have to take all the blue numbers and put them over plus or minus 2. So if I did plus or minus 1 over plus or minus 2, that would lead me to plus or minus 1/2. Plus or minus 2 over plus or minus 2, that reduces to 1. So I don't need to put that in my list because I already have 1 in my list. Then we'll need plus or minus 3 over 2. And then that'll be the last set of numbers in the list, because plus or minus 4, plus or minus 6, and plus or minus 12, if you put any of those over 2, they're all going to reduce to numbers that are already in your list. Okay, so again, what the theorem is stating is that these numbers that are in purple, the list of P over Q, it's saying that if F has a rational 0, it has to come from a number in this list. Okay, so it's like we're narrowing down all of the rational zeros that are possible for this particular function. Okay, when you started the problem, any rational 0 in the entire real number system was at play. We've now narrowed it down to these numbers that are in the list. Okay. All right, so now let's take it a step further and let's actually find which zeros do in fact work from this list. Okay, so notice I have the exact same function for f of x again. I want to find all the real zeros of the function, as well as use those to express the function in its completely factored form. Okay, so you can see I have my list of p over q values listed out as well. And basically, we're just going to test these by way of the factor theorem in order to see which ones would in fact be zeros of the function. Okay, so you could test these one of two ways. You could simply plug each one of these numbers into the function for x, simplify. If they don't give you a result of 0, then they're not zeros of the function. Okay, that gets a little tedious to do it that way. I think synthetic division is a lot better. It's more efficient to use in this process. Okay, so that's the approach we're going to take. We're going to use synthetic division until we get a remainder of 0. Okay, so we're going to make a chart here. So this is going to be kind of an abbreviated way of doing our synthetic division, since we're going to be doing the process multiple times more than likely. Okay, so I'll make this little chart here, and up here I'll put all of the coefficients of the function f. And then in the right-hand column, that's where I put the number that I'm trying to test out of my list of P over Qs. Think of the number that you're putting over to the left. It's like the number that you're putting in the box in normal synthetic division. Okay, so the first number I'm going to test is 1 from my list. All right, I'm going to bring the 2 down just like I normally would in synthetic division. I take that 2, I multiply it by the 1 that's over on the left-hand side there. And normally we would write that down, but this time we're going to keep it in our head. So 2 times 1 is 2, and now I'm going to add that 2 with 9. That's going to give me 11. Then the process starts over. 11 times 1 is 11. Add that with negative 20, you get negative 9. Negative 9 times 1 is negative 9. Add that with negative 12, we end up with negative 21. And we know that that last number is supposed to be our remainder, right? So since we didn't get a remainder of 0 here, we can rule out 1 as a 0 of the function. Okay. Since that didn't work, I move to the next number in my list, which would be negative 1. Okay. Bring the 2 down to start the process. 2 times negative 1 is negative 2. Add that with 9, you'll end up with 7. 7 times negative 1 is negative 7. Add that with negative 20, you get negative 27. And then we have negative 27 times negative 1 is 27. Add that with negative 12, we get 15. Still don't have a remainder of 0. So negative 1 is ruled out. Okay. So in this list, I can cross out plus or minus 1. Now I'll just move to positive 2 next in the list. Bring the 2 down. 2 times 2 is 4. 4 plus 9 gives me 13. 13 times 2 is 26. 26 plus negative 20 gives me 6. 6 times 2 is 12. 12 plus negative 12 gives me 0. Bingo, that's what I'm looking for. That means that 2 is a factor of this function, okay? All right, now, this is where I think synthetic division is really the better option than just evaluating f with each one of the numbers in our list, okay? So now that we've got 2 as a 0 of the function, we can start to give a slightly factored form for this function, okay? I can say that f of x factors slightly to x minus 2, right? If 2 is a 0, then x minus 2 would be a factor. And then these numbers right here of 2, 13, and 6 lead me to another factor of the 0, or of the function, okay? It would correspond to 2x squared plus 13x plus 6, okay? Notice the powers on each one of those terms, right? So the 2 corresponds to the coefficient of x squared, the 13 corresponds to x, and the coefficient on x, and then 6 is your constant, okay? So this is now a slightly factored form of f, and then what I'm going to do now is I'm going to check this quadratic to see if it factors any further, okay? Which it does. It becomes 2x plus 1 multiplied by x plus 6. And that's what we're hoping for, is that we can get everything down to linear factors. We now have 3 linear factors for the function. And these two guys of 2x plus 1 and x plus 6, they can lead me to my other 2 zeros of the function, okay? I'm going to put the first 0 of 2 that I already found for x. Then I'm also going to put negative 1/2 and negative 6. So those are all the real zeros of the function, okay? A couple other things I want to draw your attention to. Notice that I have 3 zeros, and notice that matches the power or degree of the function, okay? 3 answers, 3 zeros to match the degree of the function, okay? And again, the other thing I want you to notice is right here, this is the completely factored form of f of x. So again, not only does the theorem lead me to the zeros of the function, it's also leading me to the factors of the function, okay? Last thing I want to talk about is what if this quadratic of 2x squared plus 13x plus 6 had not factored, okay? Well, if it hadn't factored, then that tells me that the remaining zeros are not rational zeros, but are instead either irrational or complex. And how would I find those? Well, I would just use the quadratic formula on that, okay? The fact that 2x squared plus 13x plus 6 did factor tells me that the remaining 2 zeros of negative 1/2 and negative 6 are in fact rational zeros. And if you notice, negative 1/2 and negative 6 do show up in our list right here and right here. Okay, so those would have been the other 2 values in your list that would have checked out nicely. Okay. All right, so now it's your turn. You're going to practice this. There's an example on the next sheet. It's got 2 parts to it. So in the first part, you're essentially doing what we did in this example. You're going to try to come up with the zeros of the function, okay? And as well as the factored form of the function. And provided that you do all that correctly, you will then be able to sketch a graph of the function, okay? Recall when we graphed in the previous section, every function that I gave you was in factored form to start. Well, now now that we know the rational zero theorem, I don't have to give you the function in factored form. Okay, instead you can use the rational zero theorem to factor it yourself, and then you can graph it from there. Okay, so pause the video, work through that example yourself for a few minutes, and then you can come back and check your work with my own.